So, up until now, we have always talked about having numerical responses. Height, weight, price, size, something like that. Let's begin talking about how you would handle categorical responses. And for right now, we're going to talk about a category where you've got two options. Yes, no, boy, girl, left-handed, right-handed, stuff like that. So here's my data set. We went and we surveyed the gender of every child that went through Chuck E. Cheese. And we want to know, are there just as many boys in Chuck E. Cheese as there are girls? And here's our survey. Well, we can't average this. So what are we going to do? And believe it or not, we actually can use a lot of the stuff we've already learned if I change these like this. Instead of boy and girl, let's call them zeros and ones. 0 for boy, that there was no reason for that. I just needed one of them to be 0, okay? It's not like I'm making any sort of a gender statement here. I officially, legally, you know what, whatever. Point is, I have zeros and ones for my two options, okay? What would happen if I tried doing an average the way I'm used to doing it before? What I'm going to get is a whole bunch of zeros and ones that I add together until I get the number of girls over the total, right? You add these up, you're adding up the ones for all the girls, you get how many girls over the total. What that gives you is a proportion of girls. So proportions actually work the same way as averages if we're talking about ones and zeros. Proportion of girls. So it turns out that as far as doing an average or a proportion, all that's going to work the same. What's going to work a little different is the standard deviation, because the standard deviation is also in terms of the proportion. And that wasn't true before. Our standard deviation wasn't just based on X bar, it was also based on all the data. Now we can just write it in terms of the proportion, and that's going to mean a little bit of a change for us. Can you prove this? Yes. I don't want to show you the math. So instead, let's just focus on, we have 16 out of 36 that were boys, 20 out of 36 that were girls. Our proportion that we're talking about is going to be girls. Real quick, can we draw the picture of what the distribution for the proportion would look like? Well, the central limit theorem said X bar had normality, so is the proportion as well. Yes. Now, because we don't want to mix up our notation, instead of calling this X bar anymore, we're going to call it P hat. And that way we can help keep in mind, are we in the proportion scenario or the mean scenario? Okay? And instead of mu, we're going to call it P. I know we had this whole Greek theme going on, that parameters were Greek letters, but the Greek letter for P is pi. And let's be honest, if I use pi, everybody starts thinking either 3.14 or rhubarb, and then you look at the clock and realize how close it should be to lunchtime or dinner time. Actually, most people watch these videos like at 11 o'clock at night, the day the homework is due. The point is, we're not going to use pi because that's distracting. So we use P and we use P hat instead of pi and P or whatever else you might see in other notation in other books. Okay? So let's draw the picture. Can we draw a normal distribution? Central limit theorem says yes, you can. I'll prove it to you with a picture in just a second. Right here is going to be the true P, the true proportion. And this guy, it's not sigma over square root of n anymore. It's this over the square root of n. Square root of P, 1 minus P over n. Otherwise, everything's going to work the same way, which is fantastic. You don't have to learn a whole bunch of new scenarios. There is one little caveat. Let me show you what's happening with these proportions graphically. Let's say you were going to have one child. The probability that it would be 0, which is boy, it's about 50%. Probability here of it being a girl is also about 50%, even probability. Let's up this and say you were going to have 2 children. Now look how both of them being boys is not as likely as having one boy, one girl, or having both girls is less likely as well. But would you say this is normally distributed? The answer is no. It looks like 3 lines. How can you even say it's normally distributed? Well, let's say you're like me. You want to have 4 kids. Okay. Can you see how we're starting to see a shape? It's not just lines. We can actually see that there's this mound. Let's say you were going to have, my grandma had 13 kids. For 13 children, here's how it would look. Now, technically, these are lines, not entire shapes of bars, but that's the way that R has drawn it for me. Can you see how we're starting to get this nice normal distribution? That's for 13 kids. We're already getting a nice normal distribution. Let's change it now and talk about the proportion of left-hander. Here's the way it starts. If you have one child, there's a very high chance they will not be left-handed. They'll be right-handed. And a very small chance they will be right-handed. So before we were playing with a proportion that was close to half. Now we're playing with a proportion that is not close to a half. It's closer to like 0. I've got it set at 0.05, but that doesn't matter. The point is, what happens as we increase this? Let's talk about 2 children. And 2 children looks like this. So here's the probability of no left-handers, 1 left-hander, and 2 left-handers. Does this look normal? No way. And it's graphing by blowing those bars out and making them big. But watch what happens if I go 4 children. How about 5 children? How about, let's go all the way up to 13. Last time 13 made it look normal. Here, 13's not enough. It does not look normal here. Let's try having 20 kids. For 20 children, we're still seeing that skewedness. You may notice I'm zooming in a little bit. It doesn't go out to 100% anymore. If you have 20 children, the chance that all of them are left-handed, pretty rare. Let's go ahead and have 30 children. 30 was a magic number before. Can you see how we're now starting to at least get a hump? But I still wouldn't call that normally distributed. It looks more right skewed. So let's go up to having 50 kids. Okay, is this starting to look normal? Maybe let's have 75 kids. Now I'm starting to see a nice normal distribution happening here. But before 13 made it look nice, now 75 is what makes it look nice. The reason for that is because the closer your proportion is to 1 or 0, the more your sample size is going to have to be large in order for the central limit theorem to give us a nice normal distribution. What does this mean for us? Our rule up to now has always been, as long as n is greater than 30, we're good to go. Now we need a rule that not only has n, but also has p for the proportion. And so our rule is going to be that n times p has to be greater than 15, and n times 1 minus p has to be greater than 15. What do you get if you take n times p? The answer is you get the number of people who said yes, and n times 1 minus p tells you the number of people who say no. That's not a hashtag, right? Hashtag, remember when numbers used to be numbers. Number of people who said yes, number of people said no. You have to have at least 15 of both. So if you need 15 yeses and 15 nos, how large does your sample have to be altogether? The answer is 30, which is great, right? So we feel a little bit comfortable with that 30. So when you do your tests, look and see, did you get at least 15 yeses and 15 nos? If you didn't, then you have to say cannot do. It's not 30. If you sample 100 people and 99 say yes and 1 says no, that is not enough data. That's the cannot do. So our rules for proportions do change for the cannot do. The rest of it should be very similar. Let me show you some examples.